Okay, so this is 14.1. So we're going to start with vector valued functions. This chapter is vector valued functions. And this is kind of our first venture into a more complicated version of calculus than one variable calculus, but it'll still be very much based on the ideas from one variable calculus. Well, all of this class is very much based on the idea of one variable calculus, but this is a lot closer to one variable calculus than what we'll see very soon in the near future. Okay, so what's a vector value function? So the idea is a regular function from one variable calculus, f of x, right, is something, whatever, some formula of x squared plus 2x minus 3, right? So you have an input, which is a number, and an output, which is a number, right? So number r for real number r for real number, all right? So now what we're going to be looking at is a situation where your inputs are going to be numbers, and we're usually going to be using t because oftentimes we'll be thinking, most of the time actually, we'll be thinking of the input as time, all right? So this is a number, and our output is going to be a vector, all right? And so instead of just f, right, because our output is a vector, r with an arrow on top. That's our notation, okay? So we already have an example of this from the section on lines. So 3t plus 1 comma 2t comma t minus 3. That's a line. That's a vector valued function because if you give me an input t, right, I get an output which is a vector, right? So r of 2 is equal to 7 comma 4 comma minus 1, right, which is a vector. Okay, that's it. That's what a vector value function is all about. But the idea is it's going to be useful because if you think about a vector valued function, so most of the time when we actually work with vector value functions, we'll be thinking of the right-hand side as a location. So we'll be thinking of t as time. The right-hand side is a location. So it's like we're moving. So as time passes, time equals 0, time equals 1, time equals 2, time equals 3, we're going to be able to draw what we have on the right-hand side in terms of just the heads of the vectors. All right. So if I only draw the heads of the vector that's represented by the right-hand side, then I'm going to get, as we said, I'm going to get a line, right? So maybe a line like that. Okay. So what's going to happen is if I input 0, I might get an output, let's say right there, right? So let's say this is r of 0, right? R of 1 might be there, right? R of 2 will be there, and so on. Okay. What happened there? Sorry about that. And so what's happening is, as we think of this, or one of the best ways, pretty much you always want to almost think of it like this, is as you move from time 0 to time, let's say 1 second, 2 seconds, 3 seconds, you're traveling in space starting from here. After 1 second, you're here. After 2 seconds, you're here, and so on. All right? So the heads of these vectors you think of as the position of where you're at that particular time. Okay? So it's kind of a natural in that we're not really using the fact that the right-hand side is a vector in most of our visualizations or most of our applications of vector valued functions. So it's very, very unnatural, and I kind of hate it, right? Because again, technically r of 0, this guy right here, is not a point, right? It's actually technically that vector right there. R of 1 is technically that vector right there, right? R of 2 is that technically that vector right there. But again, we ignore the vector part normally in our applications and just think of the heads. And so as we move 0, 1, 2, 3, we're traveling along this line 0, 1, 2, 3. R of 0, R of 1, R of 2, R of 3. All right? Okay, it's very unnatural. I kind of hate it. That's why I said before that I really like the parametric version of the equation of a line a lot more because it's a lot more natural in terms of describing motion. But the advantage of this vector description is that when we do start to take derivatives in 14.2, you don't have this kind of weird transition from a function whose outputs are points to something whose outputs are vectors. It's more kind of consistent here, right? R is a vector valued function. Its derivative in form t2.2 is also going to be a vector valued function, all right? And so my guess as to why people always like to introduce this topic in this way, with R as a vector valued function, is so that the derivatives and stuff feel more consistent. Okay, but if you do take a lot more math, you go into this direction, there is a natural way to talk about all this that's a lot better. But for our class, this is perfectly fine. Okay, so let's talk about things which are much more complicated than just simple lines. So we're going to start. Most of my examples are going to be in the plane because the whole discussion here can be easily extended from the plane into space. Right? So when you extend from the plane to space, you're just adding a third dimension. And so in the plane, we would be talking about functions maybe like 3t plus 1 comma 2t minus 5, right? That would describe, if you think about it as motion, that would describe motion on a two-dimensional plane, right? X comma y, along a line, right? So this is going to be a line. Right. Again, it's the same exact idea as what we talked about lines in the section with lines in planes, right? When t is equal to 0, I'm at 1 comma minus 5. So I'm kind of starting out here. If we think of this as traveling in time, over time, as time passes, right? And my direction vector is 3 comma 2. So I'm kind of moving in this direction. And so as time passes, right, this is r of 0, right? Maybe r of 1 is here. Right, r of 2 is here, right? And negative time would be in the past, right? 1 second ago, we were at this location, right? We've traveled, in 1 second, we've traveled to here, and in another second, we've traveled to here, and in another second, we've traveled to here, and so on. Okay, so this guy here would describe motion in the plane, all right? So again, everything, pretty much all the ideas that we talk about in the plane, you just extend a third dimension, and you're actually talking about real life motion in the plane, right? You could describe, instead of just something moving along, right, on Google Maps, you could describe something, an airplane flying in space, flying in the air, right, where it actually has altitude, okay? All right, so that said, let's actually start with some examples. R of t equals cos t sine t. So this is one of the most important ones because it describes one of the most important kinds of motion, which is what? Well, let's take a look just by plugging in some points, just to get a very rough idea, right? So when t equals 0, we get r of t equals 1 comma 0 as a vector, right? Again, technically everything is a vector, but we're just going to mark them off as points when we're thinking of this as motion. T equals pi over 2, right? Why pi over 2? Well, because we see sines and cosines, and we know how to calculate sines and cosines of simple things like pi over 2. R of t. I guess maybe this looks a little weird. Let me put this as r of 0 here, and let me put r of pi over 2 is equal to, well, cosine pi over 2 is 0, sine pi over 2 is 1, right? So we've moved to here, right? T equals pi, we have r of pi is equal to minus 1 comma 0, right? We've moved to here, and then t equals 3 pi over 2, we get r of 3 pi over 2 is equal to 0 comma minus 1, and very interestingly, t equals 2 pi, we're back where we started. All right, so we're going from here to here to here to here and back. Right? And then, of course, as t gets bigger and bigger, we're just repeating the same motions because sine and cosine are periodic, right, with period 2 pi. And if you kind of do a more thorough graph of this, you'll see that this is, of course, circular motion. All right. So this describes motion in a circle. along a circle of radius 1, and more kind of specifically, we're moving counterclockwise in a circle about the origin. Okay. All right. So this description here allows us to describe or study circles very easily, because we can use all the techniques of one variable calculus, as we'll see in the next section. All right, so of course, plotting points like this is a nice way to kind of get a very, very rough view of what's going on. But how do I actually confirm that this is actually a circle? This is, truly motion along a circle. Well, let's take a look at this. Let me rewrite the equation just so we see it. All right, cos t sine t. Why is this on a circle? Well, this is my x-coordinate. That's my y-coordinate, right? If I take my x-coordinate squared, right, I'm going to get cos squared t plus sine squared t. What do I get? Cos squared t plus sine squared t is 1, right? So x squared plus y squared equals 1. So this particular motion, right, this description, the description of this kind of motion here, the points that I'm living at, right, in my motion, or the points where I'm at over time, always satisfies x squared plus y squared equals 1, right? My x-coordinate, my y-coordinate always satisfies x squared plus y squared equals 1. So I'm always on the circle of radius 1 about the origin. Okay. All right. Let's see. We'll look at this guy a little more thoroughly, but let me just give a few more examples just to see kind of the variety of things that that we might be working with. So another vector valued function, r of t equals t squared. All right. Okay, so a lot of times when you just see a vector valued function written out, it's hard to get a grasp as to what it might look like. So sometimes you can actually figure out a formula, and at least at this moment, hopefully we're pretty comfortable just working with formulas like this, x squared plus y squared equals 1, right? Instantaneously, when we see that, we know we're talking about a circle. Whereas perhaps when you saw cos t comma sine t like that, you didn't perhaps recognize it as a circle. So over here, t comma t squared, it's perhaps not easy to recognize what that exactly, what motion that that's describing, right? But one thing you can do is you can try to make an equation out of it, right? Doesn't always work, but if you can, oftentimes you get something which you can recognize. So in this case, what we can see, so a good thing to do it, a good way to do it is this one describes your x, that one describes your y, right? X coordinate, y coordinate. And so we have x is equal to t, y is equal to t squared, right? Now what we want is we want something in terms of x and y because we're more comfortable with that just from our years of experience in math. So what we want to do is we want to take this set of equations here and get rid of the t if we can, right? So that we only see x's and y's. And if we only see x's and y's, perhaps we'll pop out something that looks nice. And in this case, we see that we can because, well, t is equal to x. And so since y is equal to t squared, that's equal to x squared. And so ultimately, y equals x squared. All right. So this guy here, r of t equals t comma t squared, describes motion along this curve, y equals x squared. All right. What is y equals x squared? Well, just a regular parabola. X, y. All right. Let me actually not draw the arrow there. So it describes motion along the parabola. Okay. Now, one thing to note is that this y equals x squared, in a way, doesn't contain the same information that this r of t equals t comma t squared carries. In a way, this r of t carries more information because it holds information about the motion, right? Whereas y equals x squared only holds information about the shape of, let's think about this as driving, right? So y equals x squared is the shape of the road that we're moving on, all right? Whereas r of t equals t comma t squared describes actually how we're moving along that road, right? It's saying, for example, when t equals 0, I'm at 0, comma 0. So it's saying when t is 0, I'm here, right? When t is 1, I'm here. When t is equal to 2, I'm at 1, comma 4. So I'm all the way up here, for example. When t equals minus 1, I was here, right? So this vector valued function describes actual motion along the road, whereas this, again, this y equals x squared only describes the shape of the road. All right, so they're actually not, they can't be used interchangeably, but the y equals x squared does give you a lot of information about what your, perhaps the shape of your motion looks like, okay? All right, and again, we're very used to looking at things like y equals something. So if you can translate a vector valued function in terms of x and y, oftentimes we get a lot of understanding about that motion, right? Just like what we did with the circle, right? When we did, where is it? This translation from the cos t sine t to discover that that means x squared plus y squared equals 1, right? That meant we were driving along a circular road, right? But again, the cos t comma the sine t tells me more. It tells me how fast I'm driving along the road, where I'm at particular times, okay? All right, let's see. So let's actually start. So we can do all sorts of crazy stuff, right? So one advantage of describing things in terms of vector valued functions is that you can describe any curve in the plane, right? So actually, let me not even write down an equation for this. For example, if I have a curve that's described, that looks like that, right? Let's say this is a road. I'm driving along this road like this. Right? Or maybe I'm not even driving. This is just a curve, right? We want to study this curve, okay? If we wanted to do it before today, before we learned 14.1, then the only way kind of we could do it is to try to figure out an equation, right? Y equals x squared plus y squared equals 1, an equation for this guy here, right? But that equation's, well, obviously this guy is really messy and really nasty. That equation is not going to be nice, right? In particular, for this example here, the equation is definitely not going to be y equals something, because this curve here does not describe a function, right? It completely violates the vertical line test. So we cannot describe this guy in terms of a function, okay? Either in terms of x or in terms of y. Y equals something or x equals something in terms of y. So if we wanted to study this guy, one thing we could do is try to describe it in terms of a vector value function. Some guy here, some function here, right? And then, it would be more complicated. It would be complicated in a way in that we would have two things to study, right? The x of t and the y of t, right? The x coordinate depending on t and the y coordinate depending on t, as opposed to just y equals something. But the y equals something is simply never going to work. So this is oftentimes the best we can do. All right. So we would actually call this a parametrization of the curve. All right. So whenever we have a curve and we write down a vector valued function which describes motion along that curve, we call it a parametrization of the curve. Okay. And one important word here is a parametrization, as opposed to the parametrization. We would never say the parametrization because there's many ways to parametrize the same curve, all right? Just like if you have a road, there's many ways to drive along that road, right? You could drive really fast, you could drive really slow, you could start at different locations, right? You could even go backwards, right? Not so great, but you could go backwards, right? So there's many possible parametrizations for the same curve. In a later section, 14.4, we'll talk about a very important particular parametrization that is very, very natural. But for now, just think of it as there are many parametrizations, right? So you always use a parametrization, okay? All right, in any case, in order to study this horrible complicated curve, instead we study this function r of t. All right, if we could, of course, discover a formula for it. All right, so that's why this is really, really powerful. And we'll see once we get to derivatives that it might be even more powerful than it seems, because all the features, all the things that you learned in one variable calculus port over to this really, really well. Okay, more examples, right? So far we've just done stuff that are relatively simple, but you know, you could do stuff like this, t squared comma t instead of t comma t squared, right? So this would be my x, this would be my y, and so this would be x is equal to t squared, y is equal to t, and so ultimately, since y is equal to t and x is equal to t squared, that has to be y, so this describes y equals x squared, and so this describes motion along a sideways parabola. Okay, and again, in terms of this particular example, it's going to describe motion where we start here when t is equal to 0, and as time passes, we're moving that way. Okay. All right, we'll talk about very soon, in just a couple minutes, how to make it so that, you know, if you don't want to drive this way, you know, you want to drive in opposite direction, how would you change the formula, right? Well, how do you change it if you want to drive faster? How do you want to change it if you want to drive slower, and so on? Okay, but before we do that, let's actually jump into, sorry, let me write down one more. So of course, in real life, you have stuff that's much more complicated, right? E to the t, sine t, something like that, right? So this one, I'm not even going to try to figure out or draw, but I guess you could. This one's not that terrible, right? So x equals e to the t, y is equal to sine t, and this guy here tells me t is equal to natural log of x, right? And so y is equal to sine of natural log of x. All right, so that would be the equation. That would be the road that this motion is driving along. Okay. All right, but note that even though I guess these examples that I've given, you can always convert it. We've always been able to convert it to something nice. You know, whether it be x squared plus y squared equals 1 or y equals sine log of x. If I just, you know, add some crazy stuff here, you're not going to be able to do it, right? So if I just stuck in r of t equals e to the t cosine t, right? And then let's say sine t over x squared, over t squared plus 1, right? That one, you're not going to be able to figure out a nice formula, okay? So it's kind of the exception if you just randomly pick things out of your head that you'll be able to write down a nice formula. So just keep that in mind. Don't always try to look for it because sometimes you might not be able to find a nice formula. Okay, let's go to 3D. So 3D, no different. You just extend everything into the extra z dimension, all right? So one very typical first example is something like this, right? So you'll notice the first two we've seen. This is circular motion. If you didn't have the z direction, this would just be circular motion in the xy plane. But now what's happening is, as time passes, your xy position is moving around in a circle if you only look at your x and y coordinates, right? But your z coordinate, the addition of z coordinate makes it so that as you move around in a circle in terms of x and y, you're going upwards in terms of z, right? So this actually turns out to be a helix. So let's see, when t is equal to 0, I'm at 1 comma 0, so I'm starting out here, and as time passes, so I'm moving. If I looked, let me say it like this, if I looked from above x, y, and the z direction was pointing outwards toward the screen, right, and I looked at this car driving around from this formula, using this formula as its motion, then I would just see the car driving around in a circle counterclockwise like this, from a view, again, from above, right, from Google Maps or something. But again, as it's going around and around in a circle like this, it's actually moving upwards in the z direction. So it looks something in reality like this, right? As time passes, you're going higher and higher and higher, but you're always actually looping around in a circle, x and y, relative to x and y. Okay? So this is a really nice description of something that perhaps you wouldn't have been able to describe before today. All right, so this is like a helix. Okay, so something more complicated at least than just a ridiculous line or something like that. All right. By the way, if I did something like this, right, I don't have to always do, crazy strange formulas, right? If I just did something like this, that would be circular motion, and I'm always at a constant height of 3, right? So that would actually just describe motion in a circle, a circular motion with respect to x and y, but I'm always at a height 3. So this would describe maybe an airplane circling around, waiting for landing, waiting for a space at the runway, right? At a height, whatever, 3 miles above the ground. Okay. All right. Let's see. So you can do all sorts of crazy things, right? So r of t equals t squared 100 t cubed plus 5, right? Whatever. You can do all sorts of crazy things. And again, this is really powerful now, because now you're describing actual motion in the real world, right? In the real 3-dimensional world. Okay, so not just driving along a road from the Google Maps point of view, which is what the 2-dimensional version was like, right? This is actually describing motion of an airplane in the real world, or a rocket, or whatever. Okay, as time passes, of course. All right. Okay, so let's get to different parameterizations. So what happens? So let's go to our favorite example. Let's think about, so this guy here, we've said this is counterclockwise motion in a circle, radius 1, right? How do I make it go backwards, right? What if I want to describe motion going backwards, right? Well, r of t equals, you can do something like this, cosine of minus t, sine of minus t, right? So now what you've done is you've swapped the direction of time, right? So what happens is, well, let's actually simplify this. So this is cos t, comma, minus sine t, right? So this, whoa, what happened there? So this minus sine t makes it so that you're actually driving this way, right? When t is equal to 0, I'm at 1 comma 0. But now when t is equal to pi over 2, I'm at 0 comma minus 1, right? So now I'm driving to here. And then when t is equal to pi, I'm at 0, negative 1, and then here, and so on. So I'm driving actually clockwise this time. Okay. So if you replace all your t's with negative t, that's going to make you drive in the opposite direction. All right? Because in a way, you think of it as you're thinking about moving in the negative time direction. Okay. All right. How do I? So one thing we had when we had r of t equals cos t, sine t, was it took 2 pi, right? T equals 2 pi, we get back to where we started, right? How do we drive faster? Well, cosine of, let's say, 10t, comma, sine of 10t. So replace all your t's by 10t, and now you're driving actually 10 times faster, right? Because how long does it take you now to make a full circle, to come back to where you were? Well, it's when 10t is equal to 2 pi, right? And so that's so full circle when 10t is equal to 2 pi, and so t is equal to 2 pi over 10, right, equals pi over 5. So instead of taking 2 pi seconds to move around the circle, now you're only taking pi over 5 seconds to move around the circle. So you can see that that's faster. We're driving faster now. If you want to drive slower, right, multiply by 1/2 t. Okay. Again, you need to replace all your t's by 10t. Otherwise, you're going to be changing your equation. Okay. All right. So this is, by the way, these are examples of doing different parameterizations of the same curve, right? So both of these new examples here are parameterizing the same circle, right? But they're different parameterizations of the same circle, right? And again, the best way to think of it is they're different ways of driving around the circle. Okay. let's see. We can do things like shifting. R of t equals cos t. Let me write it like this: sine t, and let's say plus 3 comma 5. Right. So what is this? We're moving around a circle, right? But wherever we are, wherever we were in terms of the circular motion around the origin, now we shift over by 3 to the right and 5 up. Okay, so this should describe motion around the circle at around about 3 comma 5. Okay, so if I write it kind of in a combined form, right, cos t plus 3 comma sine t plus 5, right? So that moves the center of my circle. All right, so I can easily do modifications to move around my road. Okay. All right. By the way, how do I can actually literally see that this was actually a movement of the center of my circle, because if I think of this as x and I think of this as y, then what I have is x minus 3 squared, right? I do x minus 3 because if cos t plus 3 is x, when I subtract 3, that 3 goes, the plus 3 goes away, right? So I just get cos t. So this is cos t, right? Plus, and I go y minus 5, that gets rid of this sine t plus 5, right? It just becomes sine t squared. This becomes sine squared t. I guess I should have a square there. So I end up with cos squared plus sine squared, which is 1. Okay, so this describes motion as we expect, right? Around a circle whose center is 3 comma 5. Okay. All right, what if we want a bigger radius, right? So then r of t equals 10 cos t comma 10 sine t, right? So this is going to be, you think of it as, well, before with just cos t sine t, we were a distance of 1 away from the origin, always, right? So maybe a good way to think of this is like this, right? And now what we do is we do our circular motion, but we expand away from the origin by a factor of 10. All right. And again, if you want to think of it in terms of x and y, then we would have, let's do it like this. 10 cos t, 10 cos t would be my x, right? 10 sine t would be my y. And so x squared plus y squared would be equal to 10 squared cos squared t plus 10 squared sine squared t, which would be equal to 10 squared times 1, which is 10 squared. And so we're moving around a circle of radius 10. All right. So that expands my motion into a bigger circle. And you want a smaller circle, use 1/10 or whatever. Okay. Let's see. Now here's something. What happens if actually, let me do one more example of kind of modifying. So let's actually do a 3-dimensional example. Again, our favorite 3-dimensional example is probably the helix, right? Oops. Obviously, if you want to do a helix where you're circling around in a bigger circle, you can change the first 2 coordinates, just as we've done in the examples we just had. But let's say you want to do a helix where you're spiraling upwards faster, right? But you're still going around in a plane, in your planar motion in a way is still going at the same speed, right? What you could do is add a factor in front of the t, right? So r of t equals cos t, just the last t, right? 10t. Okay. So what this does is you're going upwards a lot faster than before, right? So before, for example, when time was pi over 2, you were at height pi over 2. Now you're at height 5 pi, right? Your xy portion of the coordinates is the same. So now you're still a helix, but you're helixing up much faster, okay? And of course, alternatively, right, if I do 1/10 t like this, or t over 10, then I'm going up a lot slower. That was a weird word, a lot slower. And so you're curling up like this. Okay. All right, you want to go backwards. Again, replace all your t's with negative t, and then you're going downwards instead. Okay, notice we only changed the last t, right? If we change all the t's to 1/10 t, then it would describe the same original helix, except driving at slower speed. Okay. All right. Now, how to parameterize? Right. So there's a lot of situations where we might start with an equation. So going backwards, kind of from what we have been doing, and get a parameterization for that equation. So, for example, a lot of times we'll start with a curve, right? Let's say the curve y equals x cubed, right? Parameterize this. Or let me write it like this, just to emphasize. So let me say find a parameterization for this guy here. Okay, and again, a parameterization, because the one that I find might be different from the one that you find, and they're both perfectly legit because they both describe motion along this curve. All right, maybe one at a faster speed, maybe one at a slower speed, whatever. Okay, so oftentimes this is the easiest situation where you have one variable in terms of the other, which is luckily for us, a lot of the situations we'll be seeing. Because then you just think about the model of t comma t squared, right? That was y equals x squared. So you want to have a formula in terms of t. So you just say, well, x is equal to t, and then you determine what y has to be from there. All right. So you start with x equals t, and then what does y have to be? Well, y always has to be x squared, right? So that means y is equal to x squared, or sorry, cubed, right? And since x is equal to t, that's t cubed. And so you know that one parameterization would be t comma t cubed. Okay, so that would describe motion along this curve right there, right? And it would describe motion in this direction, going upwards, going north. Okay, but again, you could come up with different parameterizations, right? For example, if I look at y equals x cubed, I could, for whatever reason, say this is, I want to do y equals t, right? In which case, since y is equal to x cubed, right, that means x cubed has to be t, which means that x has to be cube root of t, right? And so my parameterizations in this case would be cube root of t, comma t, right? Let me call this r. I've been using r, so p of t. Okay. So different parameterization for the same curve. Okay. All right. You definitely do want to be a little careful when you are doing this, right? Because if I tried the same thing with y equals x squared, where y is equal to t, then x would have to be square root of t. Oops. Square root of t. There's a problem here because, well, technically y is equal to t, so t is equal to x squared, so x should be plus or minus square root t, right? So if I just leave x as root t, when y is when y is negative, when t is negative, of course, there's not going to be a definition because you're going to be square rooting a negative number. And so this would actually only describe motion on this side of the parabola. All right, so you do have to be a little bit careful sometimes. All right, so if you insisted on doing it this way, where y is equal to t, then the way you would work with the parabola is to do two different parameterizations. So the first parameterization could be square root t, comma t, right? And that would describe this one. And then you would have to work with a separate parameterization for the other part of the parabola. So minus root t comma t. All right. So you would actually have to work with two separate parameterizations, which is why, of course, we like to do the one that we have been doing, t comma t squared. All right, but again, you do have options, and perhaps you might want to do it this way, depending on the context, right? If you actually have a car driving in a specific way, then maybe you have no choice but to parameterize like this. All right, in order to study the motion of that car. All right. Let's see, if you do have more complicated equations, then oftentimes it's just ad hoc. So you just take the equation that you have, whatever, x cubed equals y squared plus 4y x plus 10, right? If you want to parameterize this, you're going to have, there's no set technique for doing it, right? Because this, let me put a y here just to make it even worse. Because it's not given as a y equals or x equals. So things are perhaps not as obvious. Okay, so one thing that you can think about is how would I parameterize an ellipse? Right, so let's say x squared over 9 plus y squared over 4 equals 1. So again, this would be the ellipse, just in a plane, of course. So this is 3 here, minus 3, 2, that's a 9. Minus 2, right? How would you parameterize motion around the ellipse? So I'm going to leave this for you. But again, just think about cosines and sines, right? Why do you want to think about cosines and sines? Well, because you're doing kind of a circular-like motion. You have to do obviously some modification because you're not actually doing a circle, right? So you have to do some modifications to the just cos t comma sine t parameterization of the circle. But think about it. It's probably a good exercise. And if you can't figure it out, 99% sure the book has it, or come to the Zoom meeting on Thursday and we can talk about exactly how I would figure out how to find the equation. Okay. Let's see. So the rest of this section is just miscellaneous things for working with parameterizations and interacting them perhaps with surfaces or other things like that. So before I do anything, notice that right now we're only talking about parameterizations of curves, right? Because if you think about this in terms of motion, right, we only have one dimension, time. As time passes, right, we're describing where we are over time. Okay. In the future, towards the middle end of the class, we'll be talking about parameterizations of surfaces. And that's going to be super, super powerful for us. So the idea of parameterization is really, really important. Okay, but for now, right, we're only able to kind of describe describe curves using this technique or using this idea. Okay, so some miscellaneous stuff that you might see on the homework or something like that. Let's see, show that. So this is a nice problem. T cos t, t sine t, comma t. Let me write it kind of colloquially. Lives on the cone. Or let me say a cone. All right. Let's be more precise. Sorry. Lives on the cone x squared plus y squared equals z squared. All right. Okay. So what does this even mean? So what this means is, well, what does it mean for? Let me give this guy a name. R of t. Oh no. Okay, sorry about that. So show that this lives on a cone. What does this even mean? What this means is for a curve to be on a surface, that just means that every point, right, that's being described by this motion is actually on this surface, right? So in other words, this coordinate here, this x coordinate, comma this y coordinate, comma this z coordinate, has to be on the cone, which means this x coordinate, this y coordinate, this z coordinate has to satisfy this relationship right there. Okay? And so once we've said that, we're all set, right? So this x, that y, that z, t cos t, t sine t, and t have to satisfy the relationship x squared plus y squared equals z squared. We just check it, and then that confirms, all right? So this is basically asking, does t cos t squared, that's my x, plus t sine t squared plus, equal t squared, question mark. All right. Okay, so do the three coordinates for my motion satisfy the equation of my surface? Right? That's my x, that's my y, that's my z. And now you just, do a check, right? And this is purely algebra, okay? And either it does or it doesn't. So in this case, everything looks cool, because if you square this, you get t squared cos squared t plus t squared sine squared t. Does this equal to t squared, right? That's equivalent to asking t squared cos squared t plus sine squared t. Does this equal to t squared, right? And that's the same as asking, is t squared equal to t squared, because cos t plus sine t is equal to 1, something we'll be using quite a bit in this class. And that answer is yes, right? That guy is yes. And so therefore this guy is yes, therefore that's yes, therefore that's yes. Okay? And therefore our answer, our conclusion is yes, this r of t does live on the cone. Okay? All right, so whatever that motion describes, right, it's going to be a curve, right, that's traveling along this cone. Okay, always staying on the cone. Okay, what about this? So this is something that I think you probably saw in the homework for last week, right? Except just in terms of lines and planes. So what is the intersection of r of t equals 2 cos t sine t comma 2 and x plus 2y plus 3z equals 6, right? So again, another kind of miscellaneous type of problem. So this is asking, I have this motion in space, right, r of t, and I want to know where this curve hits the plane x plus 2y plus 3z equals 6. All right. By the way, at this point, you want to immediately recognize, when you see something like this, you should immediately recognize that that's a plane. All right, because we'll be working with planes quite a bit in this class, and you don't want to have to kind of think about it. So no powers of x, no powers of y, no powers of z, right? No interaction between x, y's, and z's, right? So this guy's going to be a plane. All right. So we've got a plane, we've got a curve, whatever it looks like. Actually, it's at constant height 2. So let's try to be at least a tiny bit accurate, right? Whatever this is, right? We want to know where it intersects the plane. Okay. All right, so maybe a kind of practical version of this is I perhaps have an equation of motion describing the position of a ball that's being thrown into the air, right? So that's going to be a three-dimensional motion in real life. And I want to know the intersection of the motion, right, the r of t, with the ground, right? So that would be the plane z equals 0. Okay. the intersection of where that motion hits the z equals 0 plane would be where that ball hits the ground, right? So you can easily think of practical examples for this kind of problem. Okay. All right. So how would we do that? Well, exactly the same idea that you used in the homework from the intersection of planes and lines, right? What does it mean to have the intersection of two objects? Well, to be on the plane, you have to satisfy this equation, right? And to be on the curve, right? You have to be there has to be a t so that you satisfy that guy there, right? So to be on both, right? The intersection is on both, so that means that 2 cos t would have to be, that's my x, right? Plus 2 times, so I'm just thinking about this second equation here. X plus 2y plus 3z is 6. And so 2 cos t plus 2 times sine t plus 3 times z plus 3 times, and z just happens to be constant here, is equal to 6, right? So I need to solve this, right? And if I can find a t that solves this, then that's going to give me points of intersection of my curve with the plane, right? And if there's no solution, it means that they don't intersect. Okay, so now I just do algebra. The rest is algebra, right? So you use whatever algebra techniques you can. And I guess I've set this up perfectly. So this is not that perfectly, but anyways, this is equal to 6. Equal to 0. And so cos t equals minus sine t. Okay, so this is actually going to intersect in an infinite number of, it's going to intersect an infinite number of times as you travel, but the number of points of intersection are actually going to be finite, right? And it's going to be the two solutions. Let's see. Cos t looks like this. Sine t looks like that. Oh no, okay. And we're looking at places where cos t is negative sine t. So our kind of base solution is pi over 4. And so it's going to be where cos t and sine t have opposite signs. It's going to be there, and it's going to be there. And so we're going to have t equals pi minus pi over 4, and t equals 2 pi minus pi over 4. Okay, so 3 pi over 4 and 7 pi over 4. And of course, in terms of, if you're actually thinking about, driving around or motion, right, it's going to also intersect at plus 2 pi plus 2 pi, 2 pi k plus 2 pi k. But we're just looking for intersection points, right? And so these two are going to represent two different points. In particular, it's going to represent the points, what was my formula? 2 cos t sine t. So it's going to be the points 2 cos 3 pi over 4, sine 3 pi over 4, comma 2. I think it was 2. Yeah. And 2 cos 7 pi over 4, comma sine 7 pi over 4, comma 2. And all the others are going to be the same intersection points. Okay. So you'll see in the homework maybe a few more miscellaneous problems that are similar in idea to this, but not necessarily exactly the same. But again, reason it out. Always when you hear the word intersection, for a surface, it means your coordinates have to satisfy the equation, and so you pretty much immediately know that you need to work with, what kind of equation that you need to work with. All right. Okay, so one problem that might be in the same style would be find the intersection of the two curves. R of t equals t cubed, and p of t equals sine of t cosine of t. Right? Okay, again, just philosophically, not philosophically, but in general in math, right? This is a problem in the plane. This is a one-dimensional object. It's a curve in the plane. This is a one-dimensional object. We're talking about a total of 2 dimensions because we're in the plane. And so we expect the intersection to be 1 plus 1 minus 2, 0-dimensional. So we expect our intersection to be a bunch of points. All right. Okay, but again, that's generically the case, but not necessarily always true. All right, and if you think about the same idea, if we were in 3D, right, if I added a third z coordinate to both of these, then we would be in 3D instead. And generically, right, the intersection would be what? Well, 1 dimension plus 1 dimension is 2 dimensions. Minus 3 is negative, right? So if it's less than 0, that means generically there's no intersection, which makes sense, right? 2 curves generically in the plane, you don't expect them to intersect. Okay. By the way, is this the only way that we have to describe, parameterization? Is this the only way for us to describe curves in space, right? So cos t, sine t, t. Is this the only way that it's possible to only possible way to describe a curve in space? Well, the answer is not necessarily. You can also describe just on the same theme as this dimensional count. You can also describe curves and surfaces as intersections of 2-dimensional, let's say, for example, 2-dimensional objects, right? Because if I have two 2-dimensional objects, right? If I have a 2-dimensional object, a 2-dimensional object, right? Maybe an equation here and an equation here, their intersection in space is going to be 1-dimensional. So it's going to be a curve, right? So that's an alternate possible way to describe curves in space. Right? So for example, a very simple situation would be 3x plus 2y plus z equals 0, x plus y plus z equals 10. This would be 2 planes, right? They're each 2-dimensional. We're in space. Oh no, I meant space here. So they're in space. Their intersection should be 1-dimensional. And in fact, we saw in last section that their intersection is a line. So you can actually describe a line instead of the way we did it in chapter 13. Instead of using a vector-valued function, you can describe a line as the intersection of 2 planes. All right? We'll actually be doing that it'll be very critical for us in the future when we do optimization. All right? So keep that in mind. It's the way we're doing it today with vector-valued functions describing curves in space is not necessarily the only way to do it. Okay. So 14 that was 14.1. 14.2 and 14.3 are going to be in the same lecture because they go together really, really well.